Alright, welcome back to physical chemistry. We're finally at the part of the course that we've been building up to all semester long. It's time to talk a bit about molecules and how quantum mechanics describes chemical bonding. We're going to begin with the simplest case that we can, a diatomic molecule. And we have to set some ground rules to make the calculations even work. And what I mean by even work is to make them such that a computer can handle them. And so we're going to begin with one of the fundamental approximations that we make. It's called the Born-Oppenheimer approximation. And this is the assumption that we can treat the motion of a nucleus as a separate issue from the motion of electrons, that we can employ separation of variables. Now, nucleus is attracted to electrons, and so their motion does depend on one another, but because nuclei are so big, they respond to forces much, much slower. They move much, much slower. And so the assumption that they're moving independently from the electrons isn't perfect, but it's close enough, and it makes the math manageable for molecular modeling, for determining how electrons are behaving from a bonding and anti-bonding and non-bonding standpoint. This doesn't work perfectly for very weak bonding and certain other molecules, and so there are chemists and physicists who are working on ways around having to do this. But for right now, there's no way to model molecules, generally speaking, without the Born-Oppenheimer approximation. If we try to, the calculations become much too large for most computers to handle. So the question that comes up next is, how would we go about writing the wave function for the electrons in a molecule? And so we'll begin with a little picture. We're going to have our s orbitals for something like the hydrogen molecule coming together, and that they can form a bonding orbital where the orbitals overlap, where they constructively interfere with one another. So the dotted lines here represent the individual wave functions, and as we bring them together, this is what happens if we add the parts that overlap. On the other hand, if a negative signed portion of an orbital comes together with a positive sign, they're going to destructively interfere, and we'll end up with no electron density in the center between, and that is an anti-bonding orbital. If we want to think of this in terms of indistinguishable, which is the idea that the wave function has to remain the same if two electrons are flipped, if they are exchanged with one another, then these two wave functions have to be equivalent. And since one of the ways that we've done that in the past is as a sum, and so we could write the electron this way, where we're taking an orbital that's created by multiplying atoms A's 1s orbital by atom B's 1s orbital, and then add or subtract that from atom A's s orbital times atom B's s orbital, where each of these numbers refers to the electron. That makes the electrons indistinguishable. In the past, we've rejected the symmetric form and taken the anti-symmetric form, and we're going to end up with an anti-symmetric wave function in the end, but not at this point. At this point, we've got two choices. For both of them are valid wave functions. The one that adds is the bonding orbital that's created by bringing these together, and the one that subtracts is the anti-bonding orbital. And so when we add the spin component in, then what we end up doing is multiplying by a spin function that relates the spin of the two electrons. But the spin function itself has to be indistinguishable as well. And so that's where our anti-symmetry is going to come in. The spin function is going to change sign under the exchange of the two electrons, and that ends up looking something like this, where we have alpha spin up, beta spin down for electron 1, the alpha, and electron 2, the beta, and then we subtract from that the switched version. And so this is basically the determinant of a 2x2 matrix. And the full wave function will have not only the spin but also the nuclear wave functions that can be written in separately. So if we assume the Born-Oppenheimer approximation, then we can put the nuclear portion out here as a separate issue. So basically what we have here is we have a wave function for a hydrogen molecule where A and B are the 1s orbitals on the two separate hydrogens. 1 and 2 are the electrons, and this is our bonding orbital, and we'd have a minus sign here if we're looking at the anti-bonding orbital. The next question then is, what does the Hamiltonian look like? And so we have to answer several questions for ourselves about the Hamiltonian. We'll begin with how many electronic kinetic energy terms. Well, we've got 2 electrons, so there's going to be 2 kinetic energy terms for those electrons. The next question is, how many electron attraction potential energy terms do we have? Now let's think about that. We've got 2 electrons. They're each going to be attracted to 2 nuclei, so that's a total of 4 potential energy terms referring to electrons being attracted to a nucleus. And then how many electron-electron repulsion terms? So since we only have the 2 electrons, there's only going to be 1 repulsion, the 2 of them for each other. But we're going to have an additional repulsion term in the Hamiltonian, that is the nuclear repulsion energy term. And so the Hamiltonian, I'm going to slide my head up here out of the way so you guys can see the Hamiltonian. The Hamiltonian looks like this. We've got negative h bar squared over 2me times the del squared operator. We've described that several times before for electron 1. So that's the kinetic energy term for electron 1. We have kinetic energy term for electron 2. Looks the same except that it's for electron 2. And then we have our attraction term. We know it's attraction because it's negative. For electron 1 to nucleus A, and electron 1 to nucleus B, and electron 2 to nucleus A, and electron 2 to nucleus B. And so each of these has a separate R, where the R is the distance between these items. The distance between electron 1 and nucleus A is this R, and so on. And then when we get to our repulsion terms, the electrons are going to repel each other based on 1 over the distance between electron 1 and 2. And the nuclei are going to repel each other based on the distance between nucleus A and B. So this works fine for hydrogen, but the next question that comes up is, what if we're looking at a larger diatomic? What if it's F2? What if it's HF? What if it's HCl? How many terms are going to be in the Hamiltonian? How would we write it out? And this is important for you guys to keep track of. There might be multiple choice questions that ask you how many terms are in Hamiltonian for HF or for CLF or something like that. How many of those are attraction terms, and so on and so on. So let's reason this out on the next slide. Move me down out of the way here and think about what this Hamiltonian is going to look like. There's going to be a kinetic energy term for each electron. So F2, each fluorine atom has 9 electrons, so there would be 18 kinetic energy terms. And then let's think about how many potential energy attraction terms there's going to be. That's described by this sum here, from 1 to n of electron attraction for a particular electron to nucleus A and electron attraction to nucleus B. So we're looking at a 2n attraction terms. Now, how many repulsion terms are there going to be? that one's going to be a double sum for the electron part, because each electron is going to be repelled by the rest. But if we just think of it as n squared, because electron 1 is going to repel electron 2 and so on, then we've got an issue there, because we'd be double counting. We'd be thinking of an electron 1 versus 2 repulsion term, and then a 2 versus 1 repulsion term. And then we'd also be counting 1 repelling 1 and 2 repelling 2 and so on. So this double sum works out to be n, where lowercase n is the number of electrons, times n minus 1. So that removes the double counting of each electron repelling itself. But then we're going to divide by 2, and that will remove the double counting of electron 1, 2 versus 2, 1. So reviewing, how many terms do we have? We have lowercase n, the number of electrons. That's how many kinetic energy terms we have for electrons. We have potential energy of attraction terms. We're going to end up with 2n of those in a diatomic molecule. And then we're going to end up with n times n minus 1 over 2. Electron-electron repulsion terms, and then we're still going to have the 1 nuclear repulsion term, since we're still just talking about a diatomic molecule. But that nuclear repulsion term is going to have these z's in here, because they are going to be multiplied by the charge on the nucleus, and that's where these z's in these attraction terms come from as well. And again, to make the math more manageable, we're going to look just at the electron terms first and save the nuclear terms for later. And so we'll remove those nuclear repulsion terms and write a Hamiltonian that looks like this. The electronic Hamiltonian, we've still got nucleus mentioned here in the electron-nucleus attraction terms. And then we've still got the electron-electron repulsion terms, as well as the electron kinetic energy terms. So we're going to pick up here in the next video and start to look at how this Hamiltonian might act on a wave function for a bonding orbital.